In the last lecture, we have started discussing method of characteristics for solving Cauchy problem for quasi-linear equations. In this lecture, we complete the proof of existence of solutions to Cauchy problem for quasi-linear equations using method of characteristics. So, outline of today's lecture is first we recall the assumptions and notations which are made about quasi-linear equations, and then we describe method of characteristics. A quick recap of lecture 2.6 where we have completed the step 1 in the method of characteristics, which is passing characteristic curves through points of gamma. Today we start elaborating on step 2 where we say what is finding a candidate solution and then show that that is indeed a solution, and then a small remark on the proof of existence and uniqueness theorem that we are going to prove at the end of the step 3. So, assumptions and notations in the context of quasi-linear partial differential equations, first order equations. This has been revisited many times, 2.1, 2.5 and as last time also in lecture 2.6. So, quasi-linear equation we denote by QL. It stands for this equation AUX plus BUY equal to C. ABC are functions, C1 functions on omega 3. Omega 3 is an open subset of R3 such that A square plus B square is not equal to 0 at every point of omega 3. And the projection of omega 3 to xy plane is denoted by omega 2. Cauchy problem, given a space curve, that is a curve in R3 which is given parametrically in this form where the parameter is running in interval I and FGH are C1 functions such that notation gamma 2 important, gamma 2 is a projection of gamma to xy plane that satisfies this condition. Gamma 2 is actually x equal to Fs, y equal to Gs as S varies in I. We want that F prime and G prime do not vanish at the same time at every point on gamma 2. Then we want to find a solution, that means a function defined on some domain such that u on gamma 2 takes the value h, which is a prescribed datum curve. Of course, we do not expect the solution domain to contain entire gamma 2, but a small portion of gamma 2 is also allowed. Now, let us look at the method of characteristics from which was discussed in the last lecture. The inspiration for method of characteristics is the following theorem which said give me a surface of the form z equal to uxy, then saying that this surface is an integral surface is same as saying that this surface is union of characteristic curves corresponding to quasi-linear equations. Since we want to construct an integral surface, in other words wants to find a solution or a surface corresponding to a solution, we will start with this idea of constructing some quantity, some object which is union of characteristic curves. That is the idea behind this method of characteristics. So, step 1 is through every point of gamma you pass a characteristic curve. So, gamma is here, we want to find a surface which contains this gamma. So, what we do is we pass through this characteristic curves like that, and you see this is going to give a surface. So, characteristic this given datum curve is described by S, and the characteristic curves for each fixed this point, this characteristic curve passing through that is defined by T in R. So, we have a description of some object, geometrical object in R3 which is parameterized by two parameters S comma T. So, as S and T vary, we hope we will get a surface, that was the idea. So, that is why we start with this step 1 where we pass characteristic curves like this. Then we say that the surface that we are going to generate would be of the following type, where the third coordinate is going to be a function of the first two coordinates. That is what we hope, and that we will achieve in the step 2. We will define a function u is a function of two variables x and y using inverse function theorem, okay. And then we show that u is indeed the solution. Step 1, what we did is finding an integral surface containing the datum curve or a piece of datum curve, means we need to weave a surface as I have just shown you in the picture, and if you weave that surface through passing curves through points of gamma and curves are characteristic curves, then that theorem gives us a hope that the surface we get is going to be an integral surface. Okay, here this is the datum curve, these are characteristic curves, this is the same picture which I have just drawn. So, for this what we do, take a point on gamma, any point on gamma looks like Fs, Gs, Hs, and then solve this system of characteristic ODE with initial conditions Fs, Gs and Hs. It means that when you look at this gamma, you take at this point Fs, Gs, Hs, the point looks like this. This is a 3 tuple, and then you pass a curve through that. That will be denoted by xts, yts, zts. This is what we get at the end of this step. At t equal to 0, it is going through this point. That is how we are solving, we are giving the initial conditions to this system of characteristic ODE. Now, by Cauchy-Lipschitz-Picard's theorem, it has a unique solution. Let it be denoted by like this: x equal to xts, y equal to yts, z equal to zts. Where is it defined? S is in I and t belongs to Js, which is an interval. Of course, the interval contains 0. Note the dependence of S on Js, that is why it is written Js. But we have seen a lemma on reparameterization which says we may take Js equal to R. So, now let us proceed to the remaining steps in this method. Second step is finding a candidate solution. How do we get that? Of course, we have to take help of this what we have been achieved so far. So, this mathematical object is described by 2 parameters and this lives in R3. So, we hope it is a surface, that is the idea. As I pointed out earlier, S represents a parameter running on the datum curve gamma, and T in R, it is parameterizing characteristic curve passing through this point on gamma which is visited when t equal to 0. Of course, gamma already lies on 1 by design initial conditions. The parameterized surface given by 1, I have put it in inverted commas here because it is not clear. It is a parameterized object is clear, surface means we expect something, that is why I put here until the confirmation comes. It is expected to be an integral surface because we were motivated by the theorem and therefore, we hope that we get an integral surface. But this is described using parameters t and s. Now, we need to write it as z equal to u of x y. So, what does this mean? It means that we would like to express the parametric surface given by 1 in this form z equal to u x y. For some function u, we need to find some function, that means we need to find a domain on which this function is defined and this holds. In other words, write the third coordinate as function of the first 2 coordinates using 1. That is the only thing that we have in our hands, namely the family of characteristic curves passing through points of gamma. So, the strategy for finding u is this: express t and s as functions of x and y we have x and y given in terms of t and s. Now suppose I write t and s in terms of x and y, go ahead and imagine this is the formula we write, t equal to capital T of x y and s as capital S of x y. Now we go and substitute in this relation z equal to z t s and define a function this way, z of t equal to capital T x y, s equal to capital S x y. So, we got some function of x y, call it u x y. This should work because z itself was motivated like that. The equation for z was derived after using that it is going to be the value of solution along the base characteristic of x t s by t s. Refer to lecture 2.6. So, therefore, it should work, but there can be very technical difficulties, we will see what they are. So, express t and s as functions of x and y like that. Recall that x and y given by x t s and y t s that together represent base characteristic curves, that is this. Now, this suggests applying inverse function theorem to this function, then you will get t and s in terms of x and y. So, if you want to apply inverse function theorem, you have to see what is the setup of the inverse function theorem. It involves a function, it involves a C1 function and certain Jacobian condition. So, we need to check all those hypotheses, then only we can apply a theorem. So, therefore, answers to the following questions will be needed. What is the domain of this function? Is the function continuously differentiable? Is the Jacobian condition satisfied? These three conditions. Usually one ignores questions 1 and 2 and just concentrate on third one at length. In fact, the third is not a condition, it is a Jacobian condition satisfied is never checked, that is put as part of the assumption and then one proves the theorem, but still 1 and 2 are still important. So, you ask this question why, you will understand later on. So, answer I will not give, you think about this question. Okay, what is the domain of this function? As we observed, for each fixed s, t varies in Js. So, it is going to be a subset of R cross I. For each fixed s, t varies in Js. Okay, that is all we can describe. It is not even clear what the set is an open set, etc. But anyway, we will do away with this kind of answering these kind of difficult questions. So, it complicates further analysis. However, we may assume without loss of generality that A is equal to j cross I, where j is a subinterval of R. I is where S is running, the parameter S is running in I, j is where the t is running. Okay, we take j equal to R, this is what we said, thanks to our lemma on reparameterization. So, therefore, we may assume that without loss of generality that A is equal to j cross I, where j is a subinterval of R. In fact, we can assume j is equal to R due to this lemma that I just quoted, reparameterization of characteristic curves, or by restricting to a small piece near gamma, that is also okay. So, you have the point P, at that point restrict to a small piece, then it is true that j can be chosen independent of S. This idea comes when one discusses differentiable dependence of or continuous dependence of solutions on the initial data. So, see the ODE book by Wolfgang. In fact, this book is a good book, we will be referring once more at least in this lecture. Okay, done. So, domain is R cross I, fine, or R cross some subinterval of I if you follow Wolfgang approach. If you follow our approach, it is R cross I. Now, next question is it C1 function? If you look at this, x and y are solutions of certain ODE, therefore, with respect to t they will be C1. What about with respect to S? What about together? Answer is yes, it is C1 function. If partial derivative with respect to t and with respect to s both are continuous functions, then it turns out that it is differentiable with respect to the two variables together. As we know, existence of partial derivatives of functions of several variables does not mean that the function is differentiable. Forget about that, function need not be even continuous at a point, but all directional derivatives exist. But if partial derivatives are continuous, then the function turns out to be differentiable. So, and it will be C1. Therefore, we are interested in xt, xs whether they are continuous functions. Xt, as I said, it is ABC, they are nice functions, so there is no problem. What about with respect to S? Where is S? S is appearing in obtaining xts and yts through the initial conditions. We solved x of 0s and y of 0s as fs and gs, and we assume f and g are C1 functions of the variable s. That is the reason why this function is C1 of j cross I. It comes from differentiable dependence of solutions to initial value problems on the parameters in the theory of ODEs. For instance, see the book by Wolfgang on ordinary differential equations. Now, let us implement step 2. Step 2 and question 3 we have to answer. Is the Jacobian condition satisfied by this function? We are interested in the invertibility of this function, right. So, we have to compute the Jacobian. Inverse function theorem says compute the Jacobian. That should be non-zero. Jacobian is this. Now, we have to compute xt at Ts, yt at Ts, xs and ys at the point Ts. Now, xt at Ts is A, it is known, yt at Ts is also known, xs at Ts is not known. What we actually know is xs at 0 comma s. That is the reason why we stick t equal to 0 now. Since we do not know the function explicitly, we cannot compute jts for an arbitrary point Ts in j cross I, which you can read it as r cross I. However, using characteristic ODE and initial conditions, because initial conditions for characteristic ODE are given at t equal to 0, therefore, there something can be done. We can compute j0s, and that is given by this. Xt, yt are solving ODEs. So, you from there you get AB. X of 0 is 0s is fs, therefore, derivative of that with respect to s is f dash of s. Similarly, ys is g dash of s. So, we want this to be non-zero. So, if you assume that j of 0 comma s naught is non-zero at a point s naught, then we can apply the inverse function theorem. I am written in the brackets local because there is something called something else called global inverse function theorem, but the usual inverse function theorem is a local inverse function theorem. Thereby step 2 will be successfully implemented. This assumption on Jacobian is called the transversality condition. The quasi-linear equation QL and the initial curve or the datum curve gamma are said to satisfy transversality condition. So, the transversality condition is two people together satisfy that, that is quasi-linear equation and initial curve. At a point S in I, if the two curves which are listed here, the first curve is a base characteristic curve. So, at point S, right. So, look at the point Fs, Gs, Hs, that is going to be on the datum curve. Through that you find the characteristic curve, project it to R2 xy plane, that will be the base characteristic curve. Thus, base characteristic curve and gamma 2, which is the projection of the datum curve gamma, these two curves intersect, of course, they intersect at the point Fs, Gs non-tangentially. That means the tangent lines do not coincide. If the transversality condition is satisfied at a point, then it will continue to hold in an interval containing S0, because the transversality condition is the non-zeroness of certain determinant, okay. And whatever is appearing inside the determinant are continuous functions of S. Therefore, at some point non-zero, it will continue to be non-zero nearby that point, that is the reason. In this case, what would happen is, imagine this is our gamma 2, that base characteristic curve will come like that. It will actually cut, base characteristic curve will not be like this. For example, it will not be like that, because here they share the same tangent. So, this is not allowed, okay. Then transversality condition is not satisfied. because if you see in the determinant, what are the two things which are coming there, the two columns. Xt yt is the tangent of the base characteristic curve, and this is the tangent of the gamma 2, and asking that this is non-zero means they are not parallel, and they are passing through this point FSGS 0 comma s, sorry, they are passing through the point FSGS, yes, and we are asking that the tangent line is not the same, that is why it is the transversality condition. So, here it is transversal, here it is not transversal. Now, if such a thing happens, if you look at nearby also, the curves are all going to be like that, right. They will always be cutting and you get a surface. That is a consequence. So, analytically the transversality condition translates to this being non-zero, this determinant. It rules out the possibility of base characteristic curves touching the projected datum curve, namely gamma 2, that we have illustrated in the picture. Touching means sharing the tangent line and coinciding, of course. Then also you have touching for a long time, okay. This is maybe at a point, but this is if it intersects along a piece of it, it means that they share tangent throughout that piece, because curve is same. So, such things are ruled out. Please spend some time on understanding this geometrically, because it will be useful when we are trying to give examples or solve or guess what would happen in certain situations for quasi-linear equations, some examples, it will help. So, this justifies the use of the word transversal, it means to cut, it cuts. So, assume that Jacobian is not 0 at the point S0. Even if Jacobian is not 0 for all s in I, j of 0 s is not 0 for all s in I, it is not going to be useful, because the only way you apply implicit inverse function theorem is at a point s equal to S0. So, I am assuming at a point it is non-zero. Of course, s equal to s naught means the point on gamma will be fs naught, gs naught, hs naught. By inverse function theorem, there exists an open subset of j cross I containing this point 0 comma s naught, and an open set on the other side omega 2 containing the point x of 0 s naught, y of 0 s naught, because our function is that, which is actually fs naught, gs naught, and a continuously differentiable function from f to e, because this should be the inverse of the function phi. So, psi circle phi will be identity on E and phi circle psi will be identity on F. These are the identity functions, okay. IE means identity. Now, we have a picture. See, this is a thing, phi we have E to F. So, originally phi is defined on some other set, which is j cross I or r cross I or j cross some I dash, and then we assume that at 0 comma s naught Jacobian condition is satisfied, non-zeroness of the Jacobian. Therefore, you can find an open set E which contains the point 0 comma s naught and an open set F which contains the image of phi under that. Whatever is the map phi we have, it maps Ts to xts, yts. So, x of 0 s naught, y of 0 s naught, which is fs naught, gs naught, and a mapping psi such that these compositions you go from E to F, come back from F to E, or go from F to E first and then come back to F, both will be identity functions. This is where we are using Ts coordinates, here we are using xy coordinates, the variables names. So, therefore, so psi of xy you denote it as Txy comma Sxy, and this equalities hold because they are inverses of each other, that will give you T equal to Txy, S equal to Sxy. As I told you earlier, ZTS was designed to be the value of the solution at this point xts, yts, refer to lecture 2.6. Therefore, this motivates us the definition of a candidate solution by this u defined on f to r given by uxy equal to z of txy sxy. As the function is a composition of two C1 functions, this is C1 inside and Z itself is C1 function, therefore, the composition will be C1 function. Therefore, U is a C1 function. Step 2 is successfully completed. We have defined what is a candidate solution. So, in lecture 2.8, that is the next lecture, we will discuss the geometric meaning of transversality condition and what happens when this condition is not satisfied. What will happen? When it is satisfied, we are going to prove a result today, and what happens if it is not satisfied will be analyzed in the next lecture. Can we still hope to solve Cauchy problem? We have to see. Answers will be in the next lecture. Now, let us proceed to step 3. What is step 3? Candidate solution which we got in step 2 is actually a solution. By definition of U, we have this formula, and ZTS equal to UXTS YTS, we also have this. Now, what is that we want to show? U solves PDE, right. So, we have to compute UX, UY, etc. But that may not be useful. Let us see. Differentiating the last equation, that is this equation, with respect to t, we get, of course, we use chain rule and we get this. Now, why did we not choose the first equation? We could have chosen that, differentiate with respect to x, with respect to y, go back and substitute in the equation and check whether it is satisfied or not. This is usually the situation all the time. Whenever we have change of variables and PDEs are there, we need to differentiate some equation, but there are always two equations for that. Only one of them would be useful in the sense it may be a quicker way of getting the solution. Okay, not wrong, other one is not wrong, but you may not be able to achieve anything with that, but this one will definitely give. You will learn this as many times as you make mistake of differentiating this U, that is true. Okay, now it is going to work. Differentiate, we got this formula. Now, XTS, YTS and ZTS are solution to Cara ODE. Therefore, here points will come out to be too long. Just to make the notation short, I am using XTS, YTS, ZTS as PTS. Now, ZT is C at XTS, YTS, ZTS, but now it is PTS. UX is as it is, XT is A at XTS, YTS, ZTS, now it is A of PTS. Similarly, the other term, we have this. So, in terms of xy in F, the last equation reads as C of xy uxy equal to ux of xy and A of xy uxy uy of bxy uxy. Done. This means U is a solution to the Quasilinear equation. Cauchy data is already taken care, we already observed that Cauchy data will be satisfied. The datum curve will be on the integral surface. So, step 3 is also successfully completed. After the 3 steps, we have obtained an integral surface defined by a function u from f to r. Of course, here we have used inverse function theorem, that means existential to start with, and S contains this point P0, S contains a piece of the datum curve near P0. In fact, that much part of gamma for which FSGS belongs to this open set F. If you could apply, if there is a global inverse theorem, if you could apply that, then we would have got a solution defined still on a subset of omega 2, but that would have contained the entire datum curve gamma. That integral surface would contain entire datum curve gamma. The solution may still not be defined on whole of omega 2. Okay, this local global we have to be very careful. What we are been dealing with is we are looking at a point on the datum curve and showing solution a surface exists nearby that, which is integral surface. That means we are discussing something like local with respect to the datum curve. And if you say global inverse function theorem, it must be giving global with respect to the datum curve, but not with respect to the domain. More on this we will see in a future lecture. Local, there are two different concepts, local with respect to datum curve, local with respect to the domain omega 2. So, theorem is here, hypothesis, Standard hypothesis on QL I am not going to recall here, and the Cauchy data. Assume that the transversality condition holds at a point S0 and denote P0 Fs0 Hs Gs0 Hs0, same thing let us call x0 y0 z0 for convenience. Conclusions: Cauchy problem has a solution defined on a neighborhood of the point x0 y0, and let d1 d2 be open neighborhoods of the point x0 y0. Let u1 u2 be defined on d1 d2 respectively be solutions to Cauchy problem, and then u1 will be identically equal to u2 on some subset of d1 intersection d2. Of course, it contains the point x0 y0. That is, solution to Cauchy problem is locally unique near the datum curve gamma. So, let us prove conclusion 1, that is precisely steps 1, 2, 3. That gives the proof of conclusion 1, that is about existence. Now, let us do the uniqueness. Let S1 and S2 be as given, one is defined on D1, other one is defined on D2, and take this point P0 which is in gamma. Now, P0 is there on gamma, it is there in S1 as well as S2, and as a consequence P0 is there on S1, P0 is there on S1. Therefore, a part of what is S1? It is an integral surface. Therefore, a part of gamma will be there on S1 intersection S2. It will be there on S1, another part will be in S2. There will be a common portion which will be there on both S1 S2, that is there. Then we have seen a corollary in lecture 2.6 in the last lecture. It said some part of the characteristic curves of QL passing through points of gamma dash will also be there on S1 and also on S2. Of course, the corollary was with respect to one surface, but here with respect to two surfaces, yes. You can see the corollary, yeah. This characteristic curve will be there on both S1 and S2. Due to transversality condition, that's why step 2 is very important. Step 2, the TS and XY, the maps phi and psi are inverses of each other, that is very important. Due to the transversality condition, any point on a characteristic curve has the form xy u1 of xy and also xy u2 of xy whenever you are in this common area F intersection d1 intersection d2. F, you remember, is the domain of definition for psi. This proves that S1 coincides with S2 in a neighborhood of P0. Hence, u1 is identically equal to u2 on some neighborhood of x0 y0. This proves uniqueness. Now, quick remark on the proof of existence and uniqueness theorem. In fact, it is going to be another proof of step 3. Step 3 was very simple, we had to simply compute the derivative, substitute. We see that the candidate solution is indeed a solution. We can give a geometric proof of that. Surface S was described using these parametric equations, right, xts, yts, zts, fine. The curves S equal to constant, what are they? They are the characteristic curves. This is gamma, fix S on this is xts. So, if S is fixed, it is a characteristic curve. Characteristic curve means what is the tangential direction? First of all, it is a curve. Therefore, xt, yt, zt is the tangential direction. So, xt, yt, zt, this is tangent, but it is characteristic curve. Therefore, the direction is actually a, b, c. Remember this, okay. And characteristic curves lies on the surface S. For S, we know something which is normal. Okay. Characteristic curves lie on S, xt, yt is also a tangential direction to S, and xt, yt, zt is nothing but characteristic direction we have observed. What is the normal? Normal is a, b, c, right? No, ux, uy minus 1, yeah, ux, uy minus 1, that is the normal. Z equal to uxy, if it is your surface, normal is along this direction ux, uy and minus 1. Okay, normal, and what is the tangential direction? One of them is ABC. that has to be 0 and this is nothing but the equation. Therefore, the surface S is an integral surface. So, any proof of the uniqueness assumption in the theorem is incomplete if the transversality assumption is not used, because uniqueness fails with the failure of transversality condition. When transversality condition fails, there are examples where uniqueness fails, there are examples where existence fails, anything can happen. So, we will discuss that later. So, if you are proving uniqueness, you must be using transversality condition is satisfied. So, people may not write this much explicitly in books, but they will say that step 2, which is what we have said, right, they make use of step 2 without explicitly mentioning to you. So, you should not get confused. The summary is that we considered Cauchy problem for QL, we proved the existence of a local solution assuming transversality condition holds, nothing, no more assumptions via method of characteristics. We proved local uniqueness of solutions, and in step 2 we noted a few possible reasons for existence of only a local solution, which will be seen in next lectures, and why we may not expect global. Global I already mentioned, there are at least 2 notions of local solutions and hence global solutions. So, in the next lecture we will take up, as promised, what is transversality condition geometrically and what happens when it fails, what are the possibilities. Thank you.